Roberts from UC Astronomy and Astrophysics. I think I might have overpromised a little bit in my abstract, so I was going to talk about a couple signatures of the late-time core collapse environment, but I realized that in 30 minutes I'm not going to be able to cover both things, so mostly this talk is going to be about proto-neutron star cooling. So before I talk about science at all, I just wanted to make sure I said thank you to the SSGF program. This has been a great opportunity, both having not having to TA while I was in grad school and also the opportunity to go to Los Alamos for the summer, which turned into a fruitful collaboration, and most of the work that I'm going to talk about today came out of that. And I also want to say thank you to the people who've collaborated with me. So Reddy, who used to be at Los Alamos, who's now at the INT, Vincenzo Sirigliano, Gang Shen, Jose Pons, and my advisor at UCSC, Stan Woosley. So once again, thank you to SSGF as well. So just a brief outline of the talk. It's mostly going to be a review because I assume most people aren't really physicists in this room. And so I'm going to give a review of the core collapse supernova, or at least the core collapse supernova mechanism, and talk some about neutron star formation and what this neutron star does over the first 10 seconds of its life. Then I'm going to talk in a little bit more detail about modeling this proto-neutron star cooling phase. So this is what we've been doing, fairly simple numerical models of this. And then I'm going to go on to talk about some specific effects that change what the cooling timescale looks like, so convection and proto-neutron star cooling, and tell you about some things we might be able to learn about dense matter from detecting a neutrino signal, and that this is related to how convection proceeds. So just as a quick review in core collapse supernova, so as I think probably most people know, stars more massive than about 8 solar masses burn all the way to iron in their core. So they go through all these hydrostatic burning phases, and you end up with iron, which of course you can't basically extract any energy from either fusion or fission. So you end up with this iron core that starts to build up, and it gets more massive and more massive as outside of the core. You burn more material to iron. And eventually this core exceeds about a Chandrasekhar mass, so basically the electrons in the core start to become relativistic. This means that this dense object in the core is unstable. Also at this point, a significant amount of electron capture starts to happen, as well as photodissociation of the iron, which removes energy from the core. And it starts to collapse. And so there's an inner region that collapses homologously, so it's in sonic contact throughout the collapse. And then there's an exterior region which collapses supersonically. And this infall continues until the homologous core reaches about 2 times nuclear saturation density or something like that, at which point the repulsive part of the nuclear interaction kicks in and halts collapse. So increases the pressure in the core. The homologous core stops as a whole because it's in sonic contact, but the supersonic material outside that's falling in slams into this core. A shock wave is born that propagates outward and eventually moves out, and most simulations now show that shock wave stops, and so it doesn't directly blow up the star, but we do know that there's a huge amount of energy released in this thing, so this has been known for, let's say, almost 90 years or something like that, that you basically get the total binding energy of this compact remnant that's left at the center. So you have something that's like 1.42 solar masses there. You can look at total gravitational binding energy of that, and it's something like 3 times 10 to the 53 ergs. And about the amount of energy that's required to blow this thing up is about 10 to the 51 ergs. So you clearly have enough energy to do this. It's just a question of how you couple that energy to the envelope. The details of that coupling are a little bit uncertain, and there's a lot of work that's being done to try to understand that coupling both at Germany and at Princeton and at Oak Ridge. But for today, we're just going to assume that they explode, and we're going to look at what happens after the explosion, what happens to this compact remnant over these first 10 seconds. So, and specifically, we're going to be looking at stars that form neutron stars, not that form black holes. So for more massive, maybe you end up directly forming a black hole in the core. So most of this neutron star's gravitational binding energy is lost in the form of neutrinos. So this cooling, so you get about 3 times 10 to the 53 ergs of neutrinos over the cooling period. And this mostly comes out actually at late time. So time scale for the whole collapse and bounce is of the order of milliseconds. And as I'll talk about in a second, the cooling time scale of the proto-neutron star is of order of 10 seconds. And so most of that energy comes out over that period of 10 seconds, not over this initial collapse and bounce phase. So, and one of the nice things about the late time signal is that it's mostly independent of all the details of the mechanism for the core collapse supernova. So as long as you know what the run of entropy and lepton fraction in this proto-neutron star is, you can sort of at least sweep some of the details of the explosion mechanism under the rug. And you can just deal with hydrostatic spherical symmetry, which means that you've reduced the complexity of the problem significantly from 3D simulations that you need to do for full core collapse. So, and the other exciting thing about this late-time neutrino signal is that it's basically going to be probing matter at and above nuclear density. So, and it's hot, but it's not really hot like you get in some laboratory experiments. So it's of order MeV. And so you might be able to, if you see a neutrino signal from a core collapse supernova, you might be able to learn something about the properties of dense matter in an environment that you really probably can't probe easily in a laboratory. And so from a I guess, a little bit different way to say what I'm saying is that this phase is reasonably well described by diffusive Kelvin-Helmholtz evolution of the proto-neutron star. And this was really first pointed out by Burroughs and Latimer in '86, and this is just the evolution of temperature as a function of time in one of their early calculations. I'll describe some things like this more. But But first, I think it's just useful to give you some order of magnitude quantities for this proto-neutron star cooling, so you get a feeling for what the scales in this problem are. So the proto-neutron star is about probably somewhere between 1.4 and 2 times the mass of the sun. 1.4 is sort of the fiducial neutron star mass. And at least after the first second, the radius of this proto-neutron star is probably something similar to a cold neutron star mass, so about 12 kilometers. You can estimate a central temperature just from the virial theorem that gives you about 30 MeV, which is reasonably consistent with what you get from a more detailed simulation. And then an interesting thing to look at is, okay, well, is this thing optically thick to neutrinos? So do neutrinos interact a number of times before they get out of the proto-neutron star? And you can do this simple calculation with sort of a standard electroweak cross-section. And you get that the optical depth is about 10 to the 3 or something like that. So this is really going to be in the diffusion limit. And you can make a simple diffusion limit estimate of what the effective emitting temperature of this thing is. So it's about 5 MeV. And that's going to mean that you're going to expect to have about 15 MeV neutrinos coming out of this thing on average. And from this, you can estimate what the neutrino luminosity is. And so that's about 10 to the 52 ergs per second. And then you can easily estimate what the time scale of this cooling is going to be. And that's going to be about 25 seconds. And so that's all great. And everything I've been telling you has sort of been more theoretical. But you know, as everyone knows, we did observe neutrinos from collapse supernova in 1987 from supernova 1987A. So we observed 20 neutrinos between 2 neutron vectors, so the IB and Kamiokanda. And the time scale over which this fell off was about 10 seconds. So you can see the count rates decreasing. And the average energies are reasonably consistent with what we just said, although obviously you're a little bit biased to higher energies because of the E-squared dependence of this interaction. So anti-neutrino capture on hydrogen. So that's nice, and you can compare it to a cooling model, and you see that it's reasonably consistent, but so these two black lines here, so this is the integrated number of events, and these stepped lines are from Kamiokanda and from the IMB, and you can compare that to these two models of proto-neutron star cooling, and you see they're reasonably consistent, although A and B are very different models, and they're both consistent with the data, so you maybe can't distinguish between particular events. But the exciting thing is that with modern detectors, instead of seeing 20 events, you'll probably see a few thousand events from a galactic core collapse supernova or a supernova in the local group, like 1987A, which went off in the LMC. So with thousands of events, you probably can distinguish between various models for the microphysics in your core collapse or in your proto-neutron star. So in addition to direct detection, There are a couple other things that, this late-time neutrino signal might significantly affect that might be observable. So there's also the diffuse supernova neutrino background. So integrated over the entire star formation history of the universe, a lot of neutrinos have been emitted in core collapse supernovae. And so there's some hope that you could observe this diffuse supernova background, supernova neutrino background with next generation detectors. And it turns out that it's actually dominated, the diffuse emission is dominated by this late time cooling. So getting a handle on what the late time spectrum looks like and what the late time emission looks like, and then integrating that over the star formation rate can give you some prediction for how sensitive your next generation detectors are going to have to be able to detect the diffuse background. One thing I've actually worked on a lot, which is sort of a different problem, but one of the input conditions for this problem is what nucleosynthesis happens very close to the proto-neutron star, and that turns out to be determined by the differences between the electron neutrino spectra and the anti-electron neutrino spectra. And so at one point this was thought to be a very promising place for the R process to occur, but our work and the work of others recently has shown that this maybe is not such a good place for the R process to happen. But it's very sensitive to what the neutrino spectra coming out of this proto-neutron star are. So those are some reasons you might want to study this thing that you don't see very often. The expected rate for core collapse supernovae in the galaxy is 2 per century or something like that. So you have to be lucky to catch one, right? So we're hoping to be lucky, I guess. So when you want to model proto-neutron star evolution, you basically have to follow how this hydrostatic object cools over time. So basically that entails coupling the general relativistic hydrostatic structure equations, so the Tolman-Oppenheimer-Volkov equations, to some sort of transport scheme for your neutrinos that takes into account that you're losing both lepton numbers, so because you're not losing the same number of electron neutrinos as electron antineutrinos, and you have to make sure that you calculate how well at what rate you're losing energy via these things. So over the summer in Los Alamos, I guess this is 2 years ago now, we wrote a code that solves the TeV equations coupled to the flux limit, equations of flux limit diffusion. So this is some approximation to neutrino transport. And then once you have this code, you can take some initial conditions, so basically just the run of entropy and lepton fraction from a core collapse simulation. And you can watch as this star the initial structure, I should mention what the initial structure of the star looks like before I go on. There's the entropy in the homologous core is very low, and this is a region where basically it's been in sonic contact throughout the collapse. Then there's a region where outside of about 0.5 solar masses where the shock is propagated through and it's been shock heated, and so then this is much hotter than the inner regions, and so then you end up with this very extended envelope, or a lot of people might refer to it as the mantle of this proto-neutron star, so outside of 0.5 solar masses. And so early on, it has a much larger radius than what a cold neutron star has. And you also have some initial lepton fraction in the star, which is basically set by at what point did neutrino trapping occur as the density got very high. And so, but usually when you start, you have some lepton fraction here, and then in the outer layers where you've had a little bit of time for neutrinos to diffuse out, you get a much lower lepton fraction. But, so over the first about 1 second, when you watch this cooling, there's a long period of contraction, and then at about 1 second here, so maybe these numbers are too small, so this is 10 to the negative 3, 10 to the negative 1, and 10. And so, but here at about a second, you've gotten to fairly close to what the cold proto-neutron star radius is. And over that first second, although you're losing a lot of energy from this outer mantle, you're also contracting. So over this period, you actually see an increase in the temperature of the outer layers. And then in the interior, but you have this spike in the temperature at early times, both here and here, from where the shock heating occurred. And you see some inward diffusion of heat towards the core. And also you get some heat from compression. Eventually, you settle down to this cold neutron star radius, and you heat the center of the core up to some maximum temperature. And then you see a period of time where cooling proceeds throughout the entire proto-neutron star. And you have, you lose lepton fraction over that period of time. So here I'm showing you, basically this is one of our calculations, this is another group's calculation, this is another group's calculation. All of these groups get these same details. I can also show you the evolution in our model, so you can see this period of time. So here I'm just plotting the neutrino luminosity as a function of time, and the radius of the proto-neutron star as a function of time, and so here time is linear. And you get this, over this first second, you get this quick contraction, and then the radius stays about the same, and you get this fall off in luminosity as a function of time. So at early times, you're at like 10 to the 53 ergs per second, but by a second, you're down at 10 to the 52, and by 20 seconds, you're down at 10 to 51 or something like that. And you also see the same behavior of the temperature I described before. If you look at the number density within the star, you can see that there's these outer layers that are at very low density, so this is this extended envelope. And as it contracts over the first second, it gets to significantly higher density. So nuclear saturation density is somewhere around here, so in the core, you're actually above saturation density throughout most of this. And here's the total lepton fraction. So initially, you have a fairly significant lepton fraction, but by, let's say, 10 seconds, you've deleptonized throughout most of the star, and you're sort of towards this, at least very close to neutron matter. Additionally, from these, but maybe the main output from these calculations for looking at what the, excuse me, for making predictions of what you're going to see with a next generation neutrino detector is what the total luminosity looks like as a function of time. So we can take these models that we've run with this flux limited diffusion transport approximation, and then we can do at least some approximation to the full Boltzmann equation, or Lindquist equation in general relativity, and look for what the luminosity evolution as a function of time looks like for basically these three different species. So nu mu's, nu tau's, and their respective antiparticles all behave basically the same way, so we sort of group those all into this nu x. And so you can see that the luminosity is actually fairly similar between flavors. You have early time, you have higher energies, and then you move towards lower energies at later times, and they all sort of start to converge. And these are sort of differential spectra, but I'm not really going to talk too much about those today. So that's the general picture of proto-neutron star cooling. But there are a lot of uncertainties in what's going on. So the question becomes, okay, what do we know well enough to be able to make some sort of prediction? What dials do we have to turn? And so, okay, of course, one thing we're interested in is what's the cooling timescale of this thing? And so that's just the Kelvin-Helmholtz timescale. And that's going to be affected potentially by things like neutrino interaction rates. So if I reduce my neutrino interaction rates, which are not well known in an interacting medium, so we know what the standard electroweak cross sections look like, but if I'm interacting with a neutron that's also interacting with some other neutrons around it, that changes what my cross sections are going to look like. And I might be able to change what my neutrino interaction rates are enough to significantly affect the timescale over which cooling occurs. It also turns out that this outer mantle that's been shock heated is convectively unstable, and this is what I'm going to talk about most for the second part of this talk. And that can actually change significantly what the gradients are and what the transport of heat and of lepton fraction are within the star. And of course, both these two things tie into what you assume for your nuclear equation of state, which is not particularly well constrained for finite temperatures and at these densities that we encounter in the star. There's also some possibility of exotic phases, which can affect whether or not your proto-neutron star is metastable. I'm not really going to talk about that today. And then, of course, there's always the caveat in astrophysics, especially when you're doing these 1D sort of things like I'm doing, is that, of course, we're not including magnetic fields, rotation. That makes the problem much more complicated. It's probably not. It's either at the limit or beyond of what you could potentially computationally do. In the models I'm talking about today, I can run on this machine I'm giving a talk on in about 20 minutes. So that the advantage is that we can survey a lot of the parameter space. So, and just quickly, I should mention what the equations of state we use. So we just use a quantum hadrodynamic mean field theory for the nuclear equation of state that's been fit to various experimental constraints. as well as observational constraints of what the sort of the maximum mass, the current maximum mass neutron star is, and what some measurements of the mass radius relationship for neutron stars are. I'm going to be talking about two sets of parameters for these equations of state today. One's going to be called GM3, one will be called IUFSU. And they have, I'll tell you why they're different here in a minute. So now I think I want to talk about maybe one of the more interesting results that's come out of this work that hopefully we're going to submit in the next week, is how convection affects this. So people will have looked at sort of the cooling without convection for a while, but no one's at least tried to mock up convection in proto-neutron star evolution over long periods of time. And that means that, okay, well, you got some answer, but convection probably significantly changes what the cooling time scale is, especially because especially both at early times and maybe at later times, because you have some total amount of energy you can get out of the star. And so this was pointed out very early when people started looking at the supernova problem, was that this stuff was unstable. And people have looked at this in detail over the first few hundred milliseconds of the proto-neutron star's evolution. So in multi-D, and there have been suggestions that there can be instabilities that are a little bit more complicated than sort of a standard Ledoux instability in the proto-neutron star. But we're going to ignore the details of this and the details of the multi-D stuff and just employ a fairly simple mixing length scheme, which is maybe not the worst thing to do. So people have done comparisons at early times, and they've looked at comparing 1D models, some sort of mixing length scheme, to multi-D models, and there's actually very good agreement between these two things. So we're pushing this out to later times when this agreement really hasn't been tested, but I think it's probably safe to do, and it's as good as you're going to do out to late times for the time being, I think. So just to give you a feeling for how convection proceeds inside this proto-neutron star, so here I'm showing you the enclosed baryon number as a function of time, and this is for this IUFSU equation of state, and this is for the GM3 equation of state. And so the regions that are colored are convectively unstable, and so you can see at early times just the outer layers are convectively unstable. As time proceeds, convection digs into the core and moves along, and then eventually the outer regions are almost always convectively unstable. But then eventually convection shuts off in the outer layers and then shuts off deeper into the star. And you can see that there's actually very different behavior of convection in these two different models, so between GM3 and IUFSU. So here it doesn't proceed all the way into the core, and maybe the more interesting thing is that it shuts off at an earlier time. So and I've color-coded these but in two ways. So there's this blued region where negative gradients in entropy are driving the instability, and gradients in lepton fraction are actually providing some sort of stabilizing influence. And then this region here, this yellowed region, is where negative gradients in lepton number are also providing a destabilizing influence. And you can see that that region never shows up here. And obviously these thermodynamic derivatives are going to be related to the equation of state, so we'd like to know what's so different between these two equations of state that creates this different behavior in the convective evolution. And so probably the most important feature, most important difference for what we're looking at between these two equations of state is the behavior of the nuclear symmetry energy as a function of density. So that's just how much the energy changes as you move away from equal number of neutrons and protons. And so here we can see that for this dashed line, which is GM3, you have, well, at saturation density, you have about the same symmetry energy, but you have a very different derivative of the symmetry energy here, which can, as a derivative of the symmetry energy with respect to density. And so that's, turns out to be a fairly significant difference. In the upper plot here, in this upper panel, I'm just showing you what the symmetry energy is at saturation density and what the derivative of the symmetry energy is at saturation density, and then plotting that versus some experimental and some quantum Monte Carlo calculations. And so this is IUFSU, and this is GM3. So you can see the derivative is very different. The symmetry energy is not so much at saturation density. So the question is, okay, well, I've sort of hammered on this difference, so how does that affect dp dyl. And so at least at 0 temperature, you can sort of, to get a feeling for what's going on, you can write down what dp dyl looks like. So there's some contribution from electrons here, this first term. And then there's a contribution here from nucleons. And you can see that having a larger symmetry energy, or derivative of the symmetry energy, sorry, with respect to the baryon density, pushes this to a more negative value. And if it's small enough, this could even potentially be positive. I should also mention that YE is always less than 0.5 in these calculations. And here I've just plotted the logarithmic derivative of this, so d ln P, d ln YL for IUFSU, so this is just gamma YL. And you can see here that, and here for GM3, and you can see that IUFSU has a much smaller gamma YL than GM, or actually has a much less negative gamma YL than GM3. And so, okay, well, this maybe is explaining to us why convection is proceeding throughout more of the star and for a longer period of time in IUFSU. So in GM3, these, with this equation of state that has a smaller derivative or larger derivative of the symmetry energy, the lepton gradients are actually providing a stabilizing influence on what's going on. So, okay, that's sort of interesting, but it's only interesting insofar as there's some observable feature that comes out of having this different behavior of convection. And so I can do a calculation of basically, given what the neutrino luminosities are, what the temperatures are, I can look at what the expected count rates for a supernova, let's say, kiloparsecs looks like in something like Super-Canyon-Conda. And I can look at this, how it evolves in time, and I can see that in this, I'm showing you here, this solid 3, and I can see there's actually a break in the luminosity at the time when convection ends in this proto-neutron star. And so in the dashed line, which is for IUFSU, there's also a break when convection ends. But because it's ending at later times, I can see there's some sort of dependence of what the time this break occurs at is based on what this derivative of the symmetry energy looks like. And you can do it for a couple other equations of state and look, and you see the same behavior. So as you increase the derivative of the symmetry energy, you actually see that this break moves backwards in time. And so maybe this is, I think that we're saying that this is a possible diagnostic of the derivative of the symmetry energy from looking at neutrino count rates. I've also showed you this dashed line here. That is just a model without any convection, and it has a very different behavior than the models with convection. And then this black solid line versus, I'm colorblind enough that I can never tell what color this is, but versus this line, those are just different models for neutrino actions. So I'm just going to put my summary of what I just talked about, because I see that it's time for questions. And I just gave you a review of this core collapse supernova mechanism in proto-neutron star formation. I told you some things about modeling proto-neutron star cooling. And I told you about some uncertain microphysics there. And then I told you some of our more recent results about convection and proto-neutron star cooling and how that might hint that you might be able to learn something about the symmetry energy from seeing core collapse supernova neutrino signal. So thank you.